Okay, welcome to my talk. Smoke and mirrors, driver signatures are optional. I'm Gabriel Landau. I am a low-level Windows engineer slash reverse engineer. I help build the Elastic Endpoint, EDR, also known as Elastic Defend. I spend a lot of my time and energy detecting malware tradecraft, so very low-level signals within the operating system, like kernel-level signals. I also spent time and energy on attack and defense of EDR, even against adversaries that have administrative privileges. I previously presented research just last month at Blue Hat Israel, ShmooCon, Black Hat USA, and Black Hat Asia. While these days I mostly wear blue, my heart will always be red. So we're going to start today talking about Windows file sharing. And when people hear Windows file sharing, they're often thinking about things like BitTorrent, or Napster, or Pirate Bay, or LimeWire, or Kazaa. But we're actually going to be talking about how files are shared between processes on the same system. So on Windows, when you want to open a file, you specify what's known as the desired access. You're going to be using an API, typically create file, which is part of the Win32 API. But if you're a kernel driver, you'll be using the native analog, which is like ZW create file. Or if you're working directly with NTDLL, you might be using NT create file. And when you're opening that file, you're going to specify the access rights. That's what you want. So if you want to be able to read the file's contents, you'll specify file read data. If you want to be able to write to the file, you'll specify file write data. If you want to be able to delete the file or rename it, you'll specify the delete access right. Simultaneously, while you're opening the file, you're going to specify what's known as a sharing mode. And sharing mode you can think of as effectively, I'm okay with others doing X to the file while I'm using it. And that might be reading the file, that might be writing the file, that might be deleting the file. And as the file is opened, your desired access is tested against the share mode of all previously granted handles to that file, currently open handles. And simultaneously, your share mode is tested against the previously granted access to all existing file handles to that file. If there is a failure in either of these tests, you'll get what's known as a sharing violation. Here's a Microsoft document talking about a bunch of different compatible sharing combinations. But there's also this concept of exclusive access. If you specify a share mode of 0, then you will have exclusive access to that file until you close the handle, according to Microsoft documentation. So when you open a file, what actually happens? Now this is an abbreviated version, but the general idea is that when you call, and this starts on the kernel side for this diagram, you start the system service routine, which is typically NT-create file, and that has to then try to parse the string, the path that you give it, C:\\/ whatever. And here at the bottom, we can see that the C: symbolic link actually resolves to \device hard disk volume 3 on this particular machine. That's the job of the object manager to do that parsing. And then once it finds the particular device to send the request to, it will then build what's known as an IO request packet, or IRP, and it will send that IRP to that device using IO call driver, and then it will go down the device stack. And this will eventually end up in the file system where we'll see here NTFS FSD create. In a little more detail here, the request here actually starts at the bottom. So the bottom of this diagram you'll see here is user mode, and we can see load library translates and ends up calling create file, and then right here NTDLL create file makes a system call, and we end up in the system service routine, which is NT create file. That transitions to the object manager, which goes to the IO manager, which goes to the filter manager, which I didn't label on the right here, and that then eventually goes to the file system. And it's the file system that's responsible for enforcing sharing. The file system works with the IO manager. It actually asks the IO manager for help in these desired access share mode checks that I was talking about 3 slides ago, to make it, and the bi-directional checks. And we can see here in the NTFS driver, NTFS check share access, and one of the things it does is it calls IO check link share access. And if that fails, then it aborts the open operation with a sharing violation. So file mappings are a way that you can actually you can modify a file even when there's no current handles open to that file. The typical flow for creating file mapping is that you would open the file, which will yield you a file handle. And then you use that file handle to create what's called a section object. And this is important terminology I'm going to be using throughout this talk. In user mode, a file mapping is called, in the kernel, a section object. They are the same thing. So create file mapping, ZW create section, they are the same function. So here, we've got a file handle, we use that to create a section, and we get a handle back. And then you map a view of that section, and what that does is it maps the file into your address space as though, and it's just memory that you can read and write at that point. If you have it open, if you can create read-only mappings, and you can create read-write mappings. And if you have a writable mapping, any changes you make to that memory will eventually get reflected in the file. The kernel will automatically flush them to that file. So in order to account for this possibility of files being modified even after all the handles have been closed, I skipped a step here. Once you have that mapped kernel view, that memory map view of a file, you're free to close the handles. So you don't necessarily have to have any open handles at this point. And so this is effectively a way to bypass that handle check we just talked about with IO check link share access, because that only works on open handles. So if you close the handles, there's nothing to check against. So in order to account for this possibility, NTFS also has to look to see that if the requester here is requesting and denying write sharing, meaning they don't want anybody else to be able to write to the file, then it has to additionally call this does file have user writable references? And what that does is it tells you whether the file can be written to via a user mode memory mapping. And if it can be, in this case, ITFS open attribute check fails. So there's an additional constraint here, and that is that Windows wants executable files to be immutable while they are in use. And by executable files or executable images, I mean EXEs and DLLs and .sys files and OCXs and CPLs and SCRs. Under the hood, they're all the same thing. They have a bunch of different extensions. They're all PE files, or portable executable files. And if you map them into memory as an executable image section, which is the way you have to do that to prepare them to actually be executed as an EXE or DLL, then while they are currently mapped, they cannot be modified on disk. So another way you could think of this is that if you were to call ZW map view of section on a sec image, meaning you've mapped the DLL or EXE into memory, that file cannot be modified until that view is removed. And so here we can see that if the requester is asking for write data and that file object is currently, there exists an image section for it, then we will call flush image section, which is a kind of a bit of a misnomer, because what this is trying to do is actually trying to destroy the image section. It's trying to say, is nobody using this image section any longer? If they're not, I'm free to destroy it. Code integrity, chapter 2. How do you trust the code that's running on your system? So Microsoft, many years back, they put out this specification called Authenticator. And it is a way to digitally sign a portable executable file. And a digital signature is a way to cryptographically attest that a file was produced by a particular entity and that the file has not been meaningfully modified since it was digitally signed. Here we can see the signature on NTOS kernel, and thankfully the signature is okay. So you can't, when you're computing an authentic signature, you can't just use a regular file hash, because signatures are often embedded into the file. And so if you were to compute the hash of a file and then to generate a signature and then stick the signature onto the file, you've now changed that file's contents and therefore changed its signature, right? Or you've changed its hash. So you kind of have a chicken and egg problem here. And so the solution to this is what's called authentihash, which is described in the authenticode specification. It's a way that describes a specific order of the file's contents, the PE file, that you're supposed to feed into the underlying hash algorithm, like MD5, SHA-1, 256, etc. And so you feed this data into the underlying hash algorithm in a certain way, and out comes what's called an authentihash. And the digital signature is actually computed over this authentihash, not the traditional file hash. But that also means that when you digitally sign a file, you're not changing its authentihash. So there's a couple implementations of authenticode in Windows. There's user mode and there's kernel mode. The user mode implementation is out of scope of this talk. The kernel implementation is called code integrity, and it resides in ci.dll in your system32 directory. This DLL contains CAs embedded into it, Microsoft Certificate Authorities, but you can't just like patch your own CAs into it and then load all the drivers you want, because the DLL is protected by the trusted boot system, which is protected by the secure boot system. So code integrity can be roughly broken down into two subsections. There's kernel mode code integrity, and that's what implements driver signing enforcement as well as the vulnerable driver block list. So driver signing enforcement states that your driver has to be signed by a certain list of signers. These days it has to be signed by Microsoft, but there's this huge backdoor with a lot of grandfathering. So Microsoft also put out what's known as the vulnerable driver block list, which is this continually growing list of drivers that are known to be vulnerable and exploited by adversaries in order to do things that even an administrator normally can't do, such as modify kernel memory. Then there is user mode code integrity. This is where CI validates the signatures on executables and DLLs before allowing them to load into user mode processes. And this is what's responsible for enforcing the protected process, as well as the protected process like signature mechanisms. Any process can actually turn on some form of UMCI if they were to turn on the Microsoft signer mitigation, which then would require that all subsequent DLLs loaded into your process be signed by Microsoft. UMCI is also responsible for the integrity check mechanism, which is used to protect FIPS 140-2 cryptographic security modules. And it's exposed to consumers as smart app control, and it's exposed to businesses as app control for business. One important note is that UMCI and KMCI, they implement different policies for different scenarios. And so what I mean by that is that the policy for protected process is different than the policy for protected process light, which is different than the integrity check policy. Chapter 3, incorrect assumptions. So I'm going to be talking about a class of vulnerabilities that result from very long-standing incorrect assumptions in the design of Windows. So Microsoft documentation implies that once you've successfully opened a file without file share right, then the file cannot be modified under you. But what if the file system doesn't know that the file's been modified? Executable images are mapped into memory, and they have to originate from PE files. So you can imagine an exe that's mapped into memory. This memory is pageable. So if there's memory pressure and the system needs free pages, these can be paged out. But the rules for paging out vary depending on the type of memory. So let's say you have a DLL, like NTDLL, and there's memory pressure and the memory manager decides to page NTDLL. Well, if a particular page has never been modified, then the memory manager is actually free to discard that page entirely, because we don't need to save a copy of a page that we already know, because we can just go to NTDLL and read it back, right? Then we don't need two copies of that same data. But if the page has been modified, so you can imagine your EDR installed a hook on some function in NTDLL, the moment that EDR wrote to that page of memory, the memory manager tracked a page fault and automatically made a private copy of just that one page, and now that page is part of the process's private working set. So that page, if it were to get paged out, would end up going to the page file. So there's two different places that that paging operations could push pages. But then when a page fault subsequently occurs, if the page has never been modified, you read it back from that original file on disk, in this example, NTDLL. But if the page has been modified, then you would go to the page file to get that private copy back. So now we're going to talk about page hashes, which are an optional list of hashes of every 4 kilobyte page of a PE file. And these allow the memory manager to validate individual pages during page fault operations, because that authentic hash is actually over the whole file, and you may not have the whole file available to you during a paging operation. So these are not official terms, but I broke them down into basically 2 flavors of page hashes. The first are what I'm calling static page hashes, and these are stored within a signature as the file is signed. You can generate page hashes with a /ph parameter to sign to, and you can see right here is the help document for it. Next is dynamic page hashes. And these can be computed on the fly by code integrity for executable image sections, such as the NTDLL, if the scenario requires it. So this gives code integrity and the memory manager some flexibility that they didn't have otherwise, because otherwise you may not be able to load a DLL on a particular scenario, because if the scenario requires page hashes, but the file was never signed with them, then you couldn't load it. This gives them a way to do it on the fly, but there's a performance cost to it. I want to add that page hashes are not free. They use CPU cycles during a page fault, and they will slow down paging operations. If you're bringing in a megabyte of data from disk, you have to hash a megabyte of data. So I'm going to give a hypothetical scenario. So let's say a ransomware operator wants to ransom an orphanage. And so they send a phishing email to the administrator of that orphanage, who loves to click buttons. And that administrator clicks enable macros and running the ransomware operator's macro, which instantly elevates using a UAC bypass, getting a full admin token. The ransomware operator wants to stomp all over the system unimpeded, but they can't because there's an anti-malware process running on the system. And Microsoft protects anti-malware processes from direct termination. They have documentation on this. The document is in fact called Protecting Anti-Malware Processes. So the ransomware operator can't kill the anti-malware process, but they want to. So could they launch themselves as a protected process, or PPL, in order to get the same privilege level as the anti-malware and then kill it? Well, no, because user mode code integrity prevents those signature checks on PPL will prevent the ransomware operator from running their malware as PPL. They don't have the right private key. Well, could they open an EXE or a DLL that's already running inside of a PPL or a protected process? Well, the answer is no, because of that immutability of executable images. And then the flush image section check I showed you before. But the problem here is that immutability check is in NTFS. So what if we move the file system to another computer? It could be SMB, so Windows file sharing is a protocol, it's a network protocol that Windows systems use to talk to each other. If you ever use a network drive, that's probably SMB. There's also Linux implementations of servers like Samba. You can even have a Python script that speaks the SMB protocol. InPacket puts out Python scripts that do this. So using SMB, an attacker is able to modify a DLL server side, bypassing the sharing restrictions in the NTFS that I just talked about. And so in this case, DLLs are incorrectly assumed to be immutable, and I'm calling this type of vulnerability false file immutability. Well, can we do this against kernel drivers? No, because they enforce page hashes. And so if we were to modify the DLL, the hash would not check out, and the page fault would fail, and the process would crash. Well, can we do it against full protected processes? The answer is no. Well, can we do it against protected process light? Yes, we can, because PPL do not implement page hashes. They do not enforce page hashes. So last year at Black Hat Asia, I disclosed the PPL fault exploit, which is pretty much what I just described to you. It is an administrator to PPL exploit, and I'm just going to briefly describe the flow, because it'll be relevant a little bit later. So the adversary, the bad guy, I'm going to call myself the bad guy here, is going to launch a PPL. In this case, I used services.exe, and I staged it such that it would load a DLL of my choosing from a storage device that I control. As that DLL is loaded, the kernel and code integrity are going to work together to try to validate that file. So they're going to read it, they're going to hash it, compute its authentihash, and then they're going to validate its signature. My storage device, upon the first request, is going to serve up the original benign DLL. After that DLL has been mapped into the user mode process, services.exe, remember it's a PPL, it's a WinTCP-like PPL, which is the highest level of highest privileged form of PPL. Then it's going to begin executing that DLL. At this point, me as the attacker, I'm going to empty the system working set. And that's going to tell the memory manager, hey, you know all those pages you just brought in? It's okay, you can throw them away. If we need them, we'll get them later, but we don't need them right now. And that means that all subsequent accesses to that DLL are now going to generate page faults and new I/O requests to my storage device. So then as with the system working set emptied, I allow the process to resume executing, and it begins to execute DLL main, which is the first thing that executes for any DLL, which generates page faults. As the page faults occur, I'm going to mostly serve up the original DLL, but I'm going to inject a payload in the form of shellcode, and that will give me arbitrary code execution as WinTCP-like PPL. If you'd like to know more, the slides and the video for this are online. So in February of this year, Microsoft added a check to mitigate PPL faults. This check involves a flag that the memory manager now sets that enforces dynamic page hashes for images, for executable images that originate from devices that are remote. This includes network redirectors like SMB, Windows File Sharing. So what is the point of this? Why did I talk about this? Well, we showed that PPL faults was able to successfully exploit bad assumptions in code integrity about the immutability of DLLs, and this allowed me to achieve unsigned arbitrary code execution as WinTCP-like. And for reasons outside of the scope of this talk, it was easy to chain this with some other non-security boundary exploits to achieve full kernel and physical memory read-write. This allowed me to compromise the entire OS, kernel included, in a couple seconds. The mitigation that Microsoft applied was narrow in scope, targeting images loaded over network redirectors. So now I'm going to be talking about some new research. I wanted to know whether I could exploit false file immutability in other ways. I wanted to look beyond executable images. I feel like I did that. Let me try something new. So I decided, what about data files? Well, before when we were talking about Authenticode, we were talking about embedded Authenticode signatures, where the signature is appended on to the end of your PE file. But there's another way to sign files. You can use what's called a security catalog. And a security catalog is essentially an array, just a long list of authentihashes with a signature at the end of it. And so you just have this signed array of authentihashes. And if your PE has a hash in that list, then you are considered to be signed by that signature. Here we can see a security catalog rendered in Windows Explorer, and if you look at the bottom here, you can actually see the authentihash files. So Windows comes with a very large list of catalogs. It depends on the version of Windows for how many catalogs it comes with. And then Code Integrity loads them into kernel memory for fast lookup, because you don't want your DLL loads to take a long time, right? So they're going to be preloaded and cached, etc. This particular system has about 2,000 catalogs, and each of these catalogs may have dozens or hundreds of hashes in it. So there's a lot of files that are signed by catalog. If we look at how security catalogs are parsed, it roughly comes down to 3 steps. First, the file is mapped into memory, and that's done with ZW open file, generic read, file share read. Next, they create a data section with ZW create section, set commit, and then they create a view, where they map a view of that data section into kernel memory. Technically, it's the system process, but we'll just call it kernel memory. So that way they can work with it as though it were just as though it is laid out on disk. So next, they validate the digital signature on the security catalog, and there's the function that's used for it. And then finally, this map file hashes function will parse the catalog and ingest it into that in-memory cache. So some key insights from that the process I just described is that they are passing file share read, but they are not passing file share write. And another way to say this is that they are denying write sharing. And this means that they are relying on that lack of write sharing to make sure that the file does not change while they are processing it. And we've already shown that this is a bad assumption. This is false file immutability. Next, they're passing sec commit to ZW create section, which is different than PPL fault, which was sec image. So what this means is they are creating a data section, they are not creating an image section, and there is no concept of page hashes for data sections. It's just the file ends up in memory exactly as it would look on disk. And so I wanted to know, could I perform a PPL fault style attack on security catalogs? So the flow is generally going to look like this. First, the attacker is going to install a security catalog that they control on a storage device that they control. And then they're going to plant a symbolic link to that security catalog in the system32 cat root directory where all those catalogs reside. Next, they're going to very politely ask the Windows kernel to load an unsigned driver, and the Windows kernel is going to try to validate the signature. It's going to not find a valid embedded signature, and then it's going to start looking at its catalog database. It's going to find that new catalog that the attacker just installed, and then it's going to proceed to validate the catalog. Again, it's going to ZW create file, ZW create section, ZW map view section. And at that point, the attacker is going to purge the system working set, telling the memory manager, all those pages that were just brought in for the signature validation, go ahead and throw them away. We'll get them later if we need it. Then code integrity is going to parse. This is the third column now from that previous slide. Code integrity is going to parse that catalog, which is going to generate additional page faults. And the attacker is going to inject their own authentic hash into that list after the signature verification phase. And this is going to allow the attacker to load a driver of their choosing into the Windows kernel, achieving arbitrary code execution in the Windows kernel. So wasn't quite as easy as last time. PPL fault was able to use an opportunistic lock, which basically let me freeze time in the victim process so I could do some things I needed to do. But I couldn't find a good opportunity here for an op lock. And so instead, I'm going to be going for a probabilistic approach. I'm going to be rapidly toggling that catalog. Benign, malicious, benign, malicious, benign, malicious, benign, malicious. And I'm going to also choose a hash near the end of the security catalog because I assume the security catalog parsing is linear. I don't actually know, but I would just assume it is. So there's a very tight race condition here. The attacker needs code integrity to trigger a page fault between that signature validation step and the parsing step. But the page is already resident because we just had to hash it in order to validate the signature. And so we need that page fault because if it doesn't happen, then code integrity is going to just ingest the benign catalog. Because And that's not what we need, right? So to evict the page, we need the memory manager to empty we need to empty the working set between those two steps, basically. And this is a very tight race. And so I'm employing multiple techniques to do this. First is I chose a very large security catalog. Most of these catalogs are like 9 to 11 kilobytes. I found one that was 4 megs. Seems good. So I picked a 4 meg security catalog. Next, I have a thread that is dedicated to emptying the system working set. That's all it does, just empties the working set again and again. Next, I have a thread that is repeatedly attempting to load that unsigned driver. And then I have one high priority CPU thread per core that is running with an above average CPU priority. And their sole purpose is to starve that thread running in code integrity of CPU quanta, or CPU cycles. So one failure mode of this exploit would be if the malicious hash is in place during the signature validation step. If this were to happen, the signature would not validate and code integrity would stop right there. Another failure mode is if an even number of swaps, including 0, occurs between the signature validation step and the ingest step, because that would mean that code integrity would ingest the benign catalog, and that's useless to us. We needed to ingest the malicious catalog. But we win as an attacker if we get CI to validate the benign catalog and then ingest the malicious catalog. So now I'm going to give a live demo. This is a non-deterministic exploit. So it may take anywhere from, well, I guess we'll see. I don't want to doom myself here. Come on, VMware. Come on, VMware. All right, so what we have here is Windows Defender. This is mpeng.exe. This is Microsoft Malware Protection Engine. And we can see on the right here that it is running as an PS-protected signer anti-malware light. And what this means is that administrators cannot kill it. So if I try to kill it, yeah, I'm sure. Access denied, even though I'm admin. So instead, I wrote a kernel driver that's going to try to do the same thing. It's just going to enumerate the system process list, and for any anti-malware protected process, it's going to try to kill it. And I call it payload driver. So when I try to run payload driver, Windows cannot verify the digital signature on this file. Well, I really thought that was going to work. So if we go and we look at the digital signature here, we can see it is signed by WDK tester. And last I checked, that is not Microsoft. So I do not have a correctly signed driver here. So what I'm instead going to do is I'm going to run an exploit. And in honor of MSRC's policy that administrator to kernel is not a security boundary, that's exactly what I'm calling it. It's not a security boundary. So here we go. So last time I was testing this, it can take between 1 and 5 runs. It's really luck of the draw here. It's non-deterministic. So I'm really hoping it works on the first try. Thank you. I'm so happy that worked. Otherwise, you just stand here and sweat. Okay, so we can see here in debug view that it killed, it said hello, right? And then it killed all the anti-malware, and the service control manager brought this service back up, and then it killed it again, right? If you are a defender and you want to know this type of attack is occurring, if you look at the Windows event log, and you look at the Microsoft Windows Code Integrity operational log, and then I press F5, we can see a bunch of errors about how it's either it's failing to load the driver because it doesn't trust it, or it's also failing to load the catalog. It doesn't trust the signature on the catalog. It depends on the failure mode of the exploit for what errors you'll see, and you'll see a combination of them. Chapter 4, avoiding pitfalls. So to avoid this type of bug, we need to understand it better. So a double read, sometimes called a double fetch, is a type of vulnerability that is common in Windows drivers. You can imagine some sort of IPC mechanism where a single page of physical memory is shared between two different processes. So let's say you have an IPC client and an IPC server, and they share a page of memory. And the way you send a request to the server is you write something to the page, and then you signal an event, and then the server wakes up and processes your packet. So here, in this example, on the right, we have the struct IPC packet, and it's got two fields. It's got a length and a data field. So in this example, the attacker would set the length field to 16, and then they would signal the server to wake up, telling it, oh, I've got a request ready for you. The server would then wake up and would read p-packet length and malloc a buffer for 16 bytes. At this point, the attacker would rapidly change that length field from 16 to 32. And then when the victim server would then try to copy the contents of the packet into that newly allocated buffer, they re-reference p-packet length. But it was 16, but it's now 32. And they end up copying 32 bytes into a 16-byte buffer, and they end up with a heap overflow. This type of problem is common in Windows kernel drivers, especially in like ioctl handlers. If you find there's a whole bunch of vulnerable drivers out there, people love to go through the ioctl handlers. But you can also have this in IPC servers too, really anywhere you have a kind of shared memory mapping, where the attacker has fast access to be able to change the memory while it's being processed. So as a call to action to developers, I want to request that you treat attacker writable files as being subject to double fetch vulnerabilities. And to understand that denying write sharing is not sufficient to prevent modification. So what's affected by this? Well, there's a couple things. First would be image sections. And how do you get to image sections? Well, you create a process, right? Create process, or you call a load library. And to mitigate against this, you would be enabling page hashes. But you might say to me, like, Gabe, why the heck would I load a library that's writable by my adversary? Well, we'll get there in a second. The next type of thing that might be vulnerable would be data sections. And so this would be if your code calls map view file. And so for this type of scenario, you would need to avoid double reads, just like the IPC scenario we just talked about. But if you don't want to go through all your code and make sure and audit it, a quick fix would be allocate a new buffer, just call malloc, and copy the file's contents to that buffer, and then work off of that copy. Don't even use the memory map version. Another option that you can do, if you don't want a second copy, would be to prevent the paging operations on that file by locking it into physical memory. And in the kernel, you can do this with mn-probe lock pages. And in user mode, you can do this with virtual lock, although I haven't tested it. But so far, I've been talking heavily about memory mapped I/O. But I want to stress that this type of vulnerability doesn't just apply to memory mapped I/O, it also applies to regular file I/O. So if you're just calling read file, you may be subject to this type of vulnerability. And so in this case, you would need to avoid double reads, and a double read with a file would be read file, seek back, read it again. Don't do that. And then the remedies for this are similar to the data section in that you need to avoid double reads, as well as copy the file to a heap buffer before processing it if you don't want to audit and rewrite your code. So what else could be vulnerable in the Windows kernel? Well, just looking across references to ZW map view section on the left, we've got a couple candidates, places that should be audited. On the right, we've got a bunch of places that are calling ZW read file, but I need to caveat here that ZW read file can be used for more than just files. It can be used on like pipe objects, for example, but there's a caveat to this caveat, and that is that attackers can trick the kernel into opening things into opening files when it doesn't think it's opening files. Using tricks like object manager symbolic links, the kernel may think it's opening a pipe when really it's opening a file. So yeah, just something to keep in mind. Looking outside of the TOS kernel, we can find a bunch more references to ZW read file and ZW map view section. And I want to stress here that I've been talking about kernel mode because the kernel interests me as an EDR dev, but this stuff applies to user mode as well. So if your code calls read file, if your code calls map view file, if it calls load library on an attacker controllable file, whereby you are denying write sharing to keep that file immutable, then you might be vulnerable because that immutability might be a bad assumption. So hypothetical example here. So let's say you have an application that's split into two components. You have a low privilege process that has network connectivity and a high privilege update service that actually installs the updates but doesn't actually do the network traffic. Right? So your low privilege process goes and downloads the updates, they're digitally signed, and puts them in like the pending updates directory or something. And then your high privilege process watches that directory, and then when files are dropped into it, it validates the signature, and if the signature checks out, and installs the update. Well, you could use false file immutability to defeat that signature check, potentially tricking that high privilege process into performing some operation that it shouldn't be doing. As far as the read file scenario, well, you might be able to cause memory corruption in an AV engine or a search indexer that has a file mapped as read-only and expects that file to not change, right? Imagine you have a PE parser in an AV engine and it's iterating the section count. It re-references the same number again and again in a for loop. Well, what if you could change that section count? Just food for thought. For the load library scenario. So before I said, well, why the heck would you load a DLL into your process that you don't control? And my answer is, the Windows kernel does that all the time. It relies on code signatures in order to validate the modules being loaded into its process. And this is also being done more and more with Windows services that are being brought under the umbrella of process protection, as well as the Microsoft Signer mitigation. Because it's possible to trick a lot of our PC servers into loading your DLLs using techniques such as system drive remapping that is out of scope of this talk. So let's talk about mitigations. MSRC is not going to service admin the kernel by default. And by service, in this parlance, we mean fixed by security update. But as a third-party AV developer, I can't fix code integrity. So what can I do to protect my customers today? And then finally, what can Microsoft do to fix it? So to mitigate, it's not a security boundary. I wrote fine, but we can still easily stop it. And fine, but we can still easily stop it is a file system mini filter driver. It looks for this scenario that is code integrity, loading a security catalog from a remote device. And I had to use some hacks and some duct tape to get it working, but that's what it looks like. It's kind of messy, and it's probably imperfect. I could probably defeat this if I really thought about it. But compare this to the 3-line fix in code integrity that I'm about to show you. So this was the diagram before about parsing, ingesting catalogs. And I propose that one fix could be to add 2 extra lines of code here. And one would be exallocate pool, which is just kernel malloc, and then RTL copy memory, which is memcopy. So by copying that security catalog out of the file mapping and into the kernel pool, we take away the attacker's ability to control it. Additionally, you would have to point your code at the kernel memory, at the kernel pool, the copy you just made. You can't just make a copy and then continue to operate off the file memory. And the next mitigation I would propose would be to allocate an MDL, and this is called a memory descriptor list, kernel stuff. But what matters here is the second one, so more so, probe and lock pages. And probe and lock pages locks these pages into physical memory such that they cannot be paged out. And by preventing them from being paged out, when the attacker attempts to empty the working set, they will succeed in emptying the working set, but these pages will not be flushed out with everything else. And that step is key to the exploit. So one thing that you could do in your environments is to enable hypervisor code integrity. Because when hypervisor code integrity is enabled, that ci.dll code I was talking about with the mapping and the validation and the parsing doesn't actually happen in CI anymore. What happens instead is that CI reads the catalog bytes and passes it over to the secure kernel, which copies it into its own heap. And at this point, we're now in that malloc mitigation I was just talking about, right? So you get all the same benefits of the malloc mitigation. So as far as disclosure goes, I reported it's not a security boundary, and fine, but we can still easily stop it, to MSRC. I suggested the EXallocate pool and mmprobelect pages mitigations that I just described, and I offered to coordinate disclosure. A week later, I asked MSRC for an update, and then about a week after that, the Windows Defender team reached out to me. They were interested in coordinating disclosure. So in the middle of April, Microsoft released a preview update with the mmprobelect pages fix, and that fix reached GA last month for desktop releases. And then 6 days later, I gave this talk at Blue Hat. So if we look inside the mitigation here, we can see the old and busted implementation called ZW creates action and then ZW map file, and then it's done. But if we look at the new hotness, we can see that those two steps happen, but then afterwards, we have this allocate MDL and mmprobelect pages. Old and busted, new hotness. So just a week or two ago, and I'm going to editorialize just a little bit here, MSRC responded to me, basically stating that it doesn't meet their criteria because administrator to kernel is not a security boundary. They weren't aware that the Defender team had already fixed the problem, but this is a common occurrence for me in doing research in the PPL and administrator space. But I want to point out that if the Windows Defender team had not stepped up, then the exploit I would be talking about today would still function. Just like last year when I did my Black Hat talk, PPL fault was still functional. I gave that talk in May of last year, and they didn't fix it till February of this year. So PPL fault was still a threat for some time. So I really, we'll get it in a second. So I just want to say it's about incentives. It took 4 months for MSRC. If we look here, I reported the vulnerability on February 14th, and they didn't get back to me until June 14th. So for 4 months, I didn't hear anything from MSRC. And this is a common occurrence for me with MSRC. This happens all the time. This right here, this is a different bug. And this is another 4 months of silence from MSRC. I know, and I'm being polite, right? Hello, being nice. My cable company is more responsive than MSRC. I don't know if they're just not sufficiently staffed or what the problem is. I've never been there, I don't know. But the response times are just not great. And it's just, I don't think it's very respectful of our time. Especially if you know it doesn't meet your rubric and you're not gonna fix it, just tell me you're not gonna fix it. Don't leave me hanging for 4 months. So, talking about incentives, a lot of these bugs eventually do get fixed. So we know that Microsoft does care about the bugs. The bugs do matter, because otherwise they wouldn't spend engineering resources fixing these things. But with these types of bugs, the researchers, they get no credit, they get no bounty, they don't get a CVE. So what is the point of reporting these bugs? We kind of have an inside joke where it's like, well, should I bother reporting this one? I know they're just gonna reject it. And if I do report it, now I have to wait how many months before proceeding, right? So I'm just wondering, can there be a middle ground between won't fix, not a security boundary, and paying out a bounty? Could there be we'll give you credit, but we won't pay you, or something like that? I just feel like MSRC is creating perverse incentives here because it's telling researchers not to report vulnerabilities that they find to MSRC. And I think James Forshaw put it brilliantly here. And the link for this article is right here. The slides will be online. This is on one of his COM to PPL articles. But I'm only going to read the last sentence here, and that is, therefore, from now on, I will not be engaging Microsoft if I discover issues which I believe to only affect protected processes and PPL. James Forshaw is arguably one of the smartest Windows researchers that I know of. And he may know of things, but he's not going to bother writing an email now because of an MSRC policy. And I just feel that that is not, it shouldn't be that way. And yeah, I'm done editorializing. So, okay. Okay. So in summary, today I introduced a new vulnerability class called false file immutability. And to motivate it, I released 2 exploits. Last year, I released a PPL fault, which as an administrator to PPL to kernel exploit, which exploits bad immutability assumptions in code sections or image sections within code integrity. I disclosed it in September of 2022, and then it was patched about 500 days later. Today, I'm going to be releasing It's Not a Security Boundary, which exploits bad immutability assumptions in data sections, reported in February of this year, and it was patched in May of this year, 90 days later. Call to action, just to repeat, is for developers to treat attacker-writable files as being subject to double fetch vulnerabilities. And remember that denying write sharing does not guarantee that the file is immutable. This is not the end of false file immutability. There are more exploits like this, and I look forward to talking about them in the future. So in conclusion, I'm Gabriel Landau. I work at Elastic Security on the Elastic Defend EDR. Any opinions expressed today are my own. They are not anything related to my employer. I want to give a special thank you to the Windows Defender team for collaborating on the disclosure and the fixing of the vulnerability. I will be releasing the POC exploit on Twitter later today, and that's my Twitter handle. And that's it. Anyone have any questions? Yes, in the back.
So instead of not engaging MSRC anymore, when you consider engaging them on your own terms, such as, here is my disclosure policy, and something saying 90 days, here's the bug, and if they refuse to respond, you are no longer working with them. They're working on your terms.
So for this round, I've been going for Google's 90+30 policy. In fact, this is why I didn't submit this and a different bug to OffensiveCon. It was because I was 88 days. I was like 90. I was just shy of the deadline, and so I think their 90+30 is reasonable, and so that's what I'm going for. So basically, if I submit an MSRC bug now, if I don't hear back from them within that time frame, that's what I'm going to go with. But if I know that they're not going to fix it because it doesn't meet their rubric, then why don't they just tell me, right? What's the point of delaying other than to frustrate me and waste my time?
Exactly.
Yeah. Any other questions? Yes.
Hey, thanks for the great talk. One, it's probably an implementation detail, but I'm really curious about how everything the system working set is implemented.
So you will be able to, if you look at the source code for PPL fault, and this is how you PPL fault right here. If you look at the source code for it, it's on my GitHub. If you just Google PPL fault, you'll find it. Yeah. It does require administrator privileges for system-wide operation. then there's actually a second step where you need to empty the standby list as well. But it was TMI, I didn't want to nerd out that much. Any other questions? Okay, thank you so much.